Imagine you're building a modern application. You've probably used APIs for everything. An API is like a waiter at a restaurant. You make a request and you wait. This is called synchronous communication. The client sends a message, the server processes it, and the client sits there doing nothing until the response comes back. It works great for simple tasks like fetching a user profile or checking a weather update. But what happens when the task takes a long time? Or what if the server is busy? In a tightly coupled system, the client is tethered to the server's availability and speed. If the server takes 10 seconds to respond, the user's mobile app hangs for 10 seconds. This is the request-response pattern, and while it's the foundation of the web, it has some serious limitations that can break your system as it scales. Let's look at a real-world scenario. In e-commerce checkout, when a user clicks Buy, the system needs to 1. Process the payment, 2. Update inventory, 3. Send a confirmation email, and 4. Notify the shipping partner. If you do all of this via standard API calls in a single chain, the user has to wait for every single step to finish. If the email service is slow or the shipping partner's API is down, the entire checkout process fails. This is a distributed monolith problem. Your services are so tightly connected that a single failure ripples through the entire stack. This blocking behavior creates a poor user experience and makes your system fragile. Why should a slow email server prevent a customer from giving you money? It shouldn't. This is where the limitations of pure API-based communication become painfully obvious.
Enter the message queue. Instead of calling a service directly and waiting for a response, the primary service sends a message to a middleman, the queue. Think of it like a post office. When you drop off a letter, you don't stand at the mailbox waiting for the recipient to read it. You drop it in, get back to your day, and trust that the post office will deliver it eventually. In software, this is called asynchronous communication. The sender, or producer, puts a task into the queue and immediately moves on. The receiver, or consumer, picks up the task when it's ready. This simple change in architecture decouples your services, meaning they no longer need to be online or fast at the exact same moment. It creates a buffer that protects your system from cascading failures and unpredictable traffic loads. To understand how this works, we need to look at the three main components: the producer, the queue, and the consumer. The producer is the service that creates the message. For example, the checkout service. It sends the order-placed message to the queue and immediately tells the user success. The queue is the buffer, a temporary storage area that holds the message until it can be processed. Finally, the consumer is the service that takes the message from the queue and does the work, like the email service or the shipping service. This architecture is called pub-sub or point-to-point, depending on how many consumers are listening. The magic here is that the producer and consumer don't even need to know each other exists. They only need to know about the queue. This abstraction layer provides incredible flexibility. One of the biggest advantages of message queues is load leveling. Imagine your app gets a massive spike in traffic, like during a Black Friday sale. In a pure API world, every request hits your backend services simultaneously. If your email service can only handle 100 requests per second, but you're getting 1,000, it will crash. With a message queue, the queue acts as a shock absorber. The 1,000 messages land safely in the queue. The consumer continues to pull them out at its own pace, 100 per second. The process might take longer, but nothing crashes. This smoothing out of traffic spikes is essential for maintaining high availability. Your system becomes resilient to bursts of activity that would otherwise take it offline. Then there's the concept of reliability. What happens if a service goes down for maintenance? In a synchronous API setup, that service is effectively missing from the system, and any requests to it fail. But with a message queue, the messages just sit there, safely persisted on disk, waiting for the service to come back online. When the service restarts, it picks up exactly where it left off, processing the backlog of messages. No data is lost. This is called guaranteed delivery. Most modern message brokers like RabbitMQ or Apache Kafka ensure that once a message is in the queue, it stays there until it's successfully processed and acknowledged.
This level of durability is nearly impossible to achieve with simple HTTP calls without complex retry logic. Decoupling also allows for horizontal scaling. If your queue is growing too fast, you don't necessarily need a bigger server. You can just spin up more consumers. Since all consumers are just pulling from the same queue, they naturally share the workload. You can scale your email service from 1 instance to 10 instances in seconds to handle a holiday rush without changing a single line of code in your checkout service. This flexibility is why message queues are the backbone of microservices. They allow each part of your system to scale independently based on its specific needs. APIs are great for communication, but queues are the secret to building systems that can grow to handle millions of users. So, when should you use an API versus a message queue? It's not an either-or situation. Use APIs when you need an immediate answer. If a user is logging in, they need to know right now if their password is correct. That's a perfect use case for a synchronous API. Use message queues for everything else: long-running tasks, background processing, or communication between internal services where an instant response isn't required. Sending emails, generating PDF reports, processing images, or updating search indexes are all prime candidates for queues. By combining the immediate feedback of APIs with the robust background processing of message queues, you create a system that is both fast for the user and incredibly resilient under the hood. In summary, while APIs are the front door of your application, message queues are the engine room. They provide the decoupling, reliability, and scalability that modern distributed systems demand. By moving from a strictly synchronous model to an asynchronous one, you protect your users from slow services and your servers from traffic spikes. Whether you use RabbitMQ, Kafka, or AWS SQS, adding a queue to your architecture is one of the single best ways to improve your app stability. Thanks for watching this deep dive into message queues. If you found this helpful, hit the subscribe button for more technical explainers. See you in the next one.